Shalom and welcome. My name is Dr. Eli Eisenberg and I'm the Senior Deputy Director General of Oort Israel. It gives me a great honor and pleasure to warmly welcome the 2012 prize winners of the Wולf Foundation. You are staying now in the Research and Development and Training Center of Oort Israel. It's a very, very unique institute, and I don't know of any other educational network, either in Israel or abroad, which has such a research and development institute, which its budget is around $25 million a year annually. I would like to thank you students, teachers, principals of Oort Israel, coming from Oort Israel schools and colleges, and also from Oort Israel headquarters staff, and of course the R&D staff of attending this wonderful event. I would like also to thank from the bottom of the heart to Dr. Liat Ben David, the Director General of Wולf Foundation. Many thanks also to Dr. Tzvi Paltiel from Oort Israel for making this event possible. Thank you very much, Tzvi. And I would like now to call Dr. Liat Ben David to say some words about the Wולf Foundation. Liat, please.
Good afternoon. Dear laureates, up till now you've heard me in English, but everything that I'm going to say you've already heard several times. So for the sake of our audience, now I'm going to present the Wולf Foundation to them in Hebrew. If you want to know exactly what I'm saying and you think I'm altering something, Professor Beckenstein will probably be able to tell you, she didn't tell us this. Shalom לכולם, אחר צהריים טובים. אני חייבת להגיד שזה כבוד והתרגשות מיוחדים בשבילי להיות פה, ואני רוצה לפתוח בראש ובראשונה בתודה רבה לאורט ישראל, לאלי, לצבי ולצבי, יש לכם שני צבי, ולכל שאר העוסקים במלאכה. אני זכיתי לעבוד עם אורט לדעתי כבר למעלה מ-20 שנה בכל הנושא של קידום חינוך מדעי וטכנולוגי, וברגע שהתמניתי למנכ"לית קרן וולף היה ברור לי שאחד משיתופי הפעולה הראשונים שאני רוצה לעשות זה עם אורט ישראל, ומצאתי פה כמו תמיד בית חם ודלת פתוחה. אז תודה, ואני מקווה שזו סנונית ראשונה לעוד הרבה הזדמנויות. כשאני עשיתי את הדוקטורט שלי לפני 20 שנה במדעים, סיפרו לי שהמנחה שלי הוא זוכה פרס וולף, ושזה אומר שהוא מחכה לטלפון מסטוקהולם לקבל גם את הנובל. עכשיו ידעתי מה זה נובל, ואני מניחה שגם אתם יודעים, אבל מה זה וולף לא היה לי מושג. אז אני רוצה לספר לכם ממש בכמה מילים קצרות, מהי קרן וולף, כיצד היא נוסדה ומה המטרות שלה, ולמה בעצם אנחנו פה היום. דוקטור ריקרדו וולף היה ממציא, מדען, שבעצם המציא דרך למחזר מתכת מדוודים גדולים שבהם עשו כל מיני תהליכים, ומכך הוא נולד בגרמניה בסוף המאה ה-19, ומכך הוא עשה את הונו. בשנות ה-20 הוא עבר לקובה, שם הוא המשיך לעשות את מה שהוא עשה, אבל בין שאר הדברים הוא היה חבר טוב של אחד בשם פידל קסטרו. אני חושבת שאפילו הצעירים בקהל יודעים שזה שם מוכר, והיה לו מזל להיות חבר שלו, הוא עזר לו במהפכה שלו. ולכן כשקסטרו ניצח את המהפכה בשנת 59, הוא פנה אל דוקטור וולף ואמר לו, מה אתה רוצה שאתן לך עד חצי המלכות? דוקטור וולף הסתכל עליו, ובהיותו יהודי וציוני, אמר לו, אני רוצה להיות השגריר שלך במדינת ישראל החדשה. וכך הוא בא לפה עם כל כספו ועם אשתו, והיה השגריר של קובה, עד שקובה נתקע את יחסיה, ואז הוא החליט להישאר כאן. הוא נשאר פה בעצם עד סוף חייו, הוא נפטר בגיל 94, היו לו חיים ארוכים ומלאים. לקראת סוף חייו הוא החליט לתרום כמעט את כל הונו למדינת ישראל, באמת מתוך תפיסה ציונית פילנטרופית של תרומה, שאמרה, אני רוצה שלמדינת ישראל, כמדינה היהודית, שהיא תהיה מדינה שאכן ממלאת את דברי הנביאים אור לגויים, אבל בדרך שמציינת את הטובים שבטובים בעולם בתחומי המדעים והאומנויות. בלי הבדלים של דת, גזע, מין, מדינה, גישה פוליטית, צבע עיניים או מספר נעליים. הטובים שבטובים במדע ובאמנויות, אנחנו ניתן להם פרס, בדיוק כמו שעושה נובל. זאת מערכת של פרסים, ומאז 1978 קרן וולף נותנת פרסים למדענים ולאמנים המובילים בעולם, ב5 תחומי מדעים ו3 תחומי אמנויות, ברוטציה קבועה. יש לנו כבר למעלה מ-270 זוכים, 5 מהם, אלה של השנה, נמצאים עמנו פה היום. בתחומים המקבילים לנובל, למעלה מ-33% מהזוכים שלנו מקבלים אחר כך פרס נובל. כולל הישראלים, עדה יונת, אברהם הרשקו ודני שכטמן, שכולם בוודאי מכירים את השמות שלהם. אבל זוכים אחרים שלנו הם סטיבן הוקינג, הפיזיקאי, מרק שגל, הצייר, זובין מטה, יצחק שטרן ועוד כהנה וכהנה. מה שאומר שיש סיכוי טוב שאחד מאלה שתשמעו היום, אולי עוד תשמעו עליו גם בעתיד. אבל כמובן שזה לא הדבר היחיד שקרן וולף עושה מבחינה, זה לא רק לחלק פרסים. קודם כל אנחנו מחלקים אותות מצוינות על פני רצף. עוד מעט אתם תגיעו, אני מקווה, לאוניברסיטאות, והטובים שבטובים שבכם יוגשו על ידי האוניברסיטאות לקבלת מלגת וולף, למצוינים, לתואר השלישי. לאחר מכן, אם תבחרו לחזור אחרי פוסט דוקטורט בחול, ולהתחיל את העבודה שלכם באחת המעבדות בארץ, יוכלו להגיש אתכם בתור מצטיינים, לקבל את פרס קריל, שגם הוא ניתן מטעם קרן וולף. ואחרי כן, וולף ונובל. אחת המטרות שלנו היום בקרן היא לקחת את כל גוף הידע הזה שנמצא בידי הזוכים שלנו, שזה באמת הידע המוביל בעולם בתחומים שלהם, ולהפוך אותו לזמין, ולזמין בראש ובראשונה לכם. מי כמונו פה בחדר הזה יבין, כשאני אומרת שאחת התכונות ואחד הערכים המרכזיים שלנו כעם, זה והגדת לבנך. הכוונה היא להמשיך את הסיפור, לדעת להעביר מדור לדור את השרביט, את המוטיבציה ואת הערך של מצוינות, ובגלל זה אנחנו פה היום. אז שוב תודה לאורט, ואני רואה שהצטרף אלינו צבי פלג. בבקשה.
Thank you very much, Liat. And I would like to invite our Director General, Mr. Tzvi Peleg of Oort Israel. Thank you. צביקה פלג, בבקשה.
שלום לכולם. אני אתחיל בכמה מילים באנגלית, ולאחר מכן אני אעבור לעברית. Dear Wolf Prize winners, Oort Israel teachers, students, and all our guests, with great pleasure and excitement, I welcome the Wolf Prize winners to Oort Israel Research Development Mushinsky Center. Oort Israel is a leading educational school and colleges network in Israel. We educate 10% of all high school students in Israel in our 201 schools and colleges all over the countries. We serve all the population in Israel, which means Jewish, Muslims, Druze, Bedouin, all the population that are Israeli citizens, we serve them in a great love and great devote. Oort Israel mission is twofold. First, we inculcate in our students Jewish and general moral values with major emphasis on the practice of giving back to one's society. Many of our students volunteer in their communities throughout the year. Second, our school are characterized by their science technology tracks. More than 60% of students study various tracks in science technology. All these tracks are developed here in this building in the Mushinsky Center. And what is why we are so happy that you, the Wolf Prize winners, honored us in your presence and willingness to share some of your ingenuity with our students, with the hope that maybe some of them will become a scientific like you and someday even win the Wolf Prize. Especially I want to thank to Dr. ליאת בן דוד. לומר כמה מילים בעברית, אני חושב שמצוינות זה ערך. אני חושב שרשת אורט ישראל עם 100,000 התלמידים שהיא משרתת מדי שנה, הייתה חייבת להוביל את אותם שני דגלים שהזכרתי, דגל הערכים כדגל ראשון בעשייה החינוכית. אין מצוינות ללא ערכים, אין מצוינות ללא מורשת, אין מצוינות ללא זהות יהודית. ואני אומר את הדברים בצורה מאוד מאוד חד משמעית. אנחנו כולנו חייבים קודם כל לדעת מאין באנו ולמה אנחנו כאן, וביד השנייה לנסות ולהיות מצוינים בשדה המדע והטכנולוגיה. אני חושב שאת אותם שני דגלים עליהם אני מדבר, אתם חייבים לקחת איתכם לאורך כל הדרך. כי בלי אהבת אדם, בלי היכולת לתת, קשה מאוד לבנות עם במדינת ישראל. והייחודיות שלנו כאן במדינה הקטנה הזאת, היא להיות מצטיינים במדע וטכנולוגיה מחד, ולהיות ערכיים ומושרשים מאידך. אני רוצה להודות לקרן וולף על שיתוף הפעולה, אני רוצה להודות לחבריי במטה, דוקטור אלי אייזנברג והצוות, ואני רוצה להודות לכם, מורים ותלמידים, על שאתם בדרככם בוודאי תובילו את תלמידי אורט ישראל, מדינת ישראל, לאיכות ומצוינות, כדי שנמשיך להיות לא רק אור לגויים, אלא גם אורט לגויים. תודה רבה.
Okay, so now with no further ado, we will start. You have these brochures, and we are going to go according to the order of the people that are listed in them. The format that we're going to work upon is a very, what we call short TED presentations. Each one of the laureates is going to be invited up here. He will give a short 8-minute talk, and then you will have approximately 4 minutes to ask questions. Ask questions, please. I encourage you to do so. Okay, so we're going to start with Professor Paul Alivisatos from the University of California at Berkeley in California, who won the prize for developing the okay, Paul, you're going to have to teach me how to say this. Colloidal inorganic nanocrystals, and utilizing their unique properties for applications. Was that correct? Okay, thank you. Paul, please.
Okay, thank you. So there's a joke about the 5-minute university. The 5-minute university is where you learn in 5 minutes everything which, if you go to a regular university, it's all you will remember 5 years after you finish your degree. And here we have 8 minutes, so we can do an advanced degree. So we're going to do nanoscience in a few minutes. We're going to learn scaling laws, building blocks, the power of one, deep biology connection, and what it is that we build today. So let's do it. So I don't know if you've ever heard of the philosopher Democritus. He's an ancient Greek philosopher, and he was the first one to realize that there could be something called atoms. And his idea was the following. Imagine that you take a piece of gold and you chop it in two. And you say, okay, what will be the properties of the two pieces that you chopped? And you would say, well, all the basic properties will probably be the same. If I measure the melting temperature, if I measure how hard it is, it'll just be two small pieces of the same basic material. But he thought, well, I'll chop it again and again and again, and I'll just keep chopping it as many times as I can. And eventually it may get down to something so small which it can no longer be divided, which in Greek is that which cannot be divided, is the atom. Atom means can't break it anymore. And what's interesting is, first of all, that he thought of that, but secondly, that if you take matter and you chop it in two many, many times, actually at some size the properties become very different. So if you have a piece of bulk matter or an atom, in between there are these small nanoscale objects, and every time you chop them in half, every one of their basic properties completely changes. So its temperature for melting, its temperature, the hardness, its energy levels, they all change as a function of the size. And that's what the science that I'm involved in concerns. You see this every day in your computers. Every day in the computer, every 18 months, the features in the computer are twice as dense. And so that's a version of Democritus's experiment. In fact, today in modern electronics, we see many of the quantum effects that show up in finite-sized systems. So here's a list of scaling laws. A scaling law is how the property of matter will change when you change the size of the basic components. And I'll show you some examples of those as we go along. Now, when I started working in this area, there were many people who were making semiconductor materials in these very big vacuum chambers where they would purify everything and make it super controlled. And my job, working at that time at Bell Laboratories with some friends, Louis Bruce and others, was in a corner there to try to do the same thing in a little tiny flask that would look just like a regular beaker, like what you might have seen in your chemistry lab. So to try to make an advanced semiconductor material in a very low-tech environment. And in fact, one of the first people I met when I was just beginning my career as a scientist was a very famous theoretical physicist, and I went to talk to him about this project, and he said, this probably won't work. You should abandon your project because the materials you'll work with will be very impure. So I'm going to try to tell you a story of how we could use very low-tech stuff to make very high-quality material. I mentioned to you the scaling laws. Here you see how the temperature for melting depends upon the size for a piece of semiconductor. So you take a piece of silicon and you chop it in two, and it becomes, if it's only 30 atoms across versus 15 versus 5, and you measure the temperature at which it melts, it actually starts to really drop off as a function of the size. That's because the atoms all bond to each other, but on the surface they don't have anything to attach to. So the whole crystal becomes weaker when so many more of the atoms are at the edge than are in the interior. And for that reason, as the crystal becomes very small, it melts at lower and lower temperature. That's an example of a scaling law. Very important one for us. Here's another scaling law. Many of you one day will hopefully go to the jewelry store to buy a diamond ring to give to somebody that you want to get married to. And when you go, you'll find very quickly that the price of the diamond you can afford is very specific. You have a certain amount of money, that's a certain size of diamond, okay? In fact, there's on the De Beers website, it says, big diamonds are much rarer, so a diamond of double the weight costs 4 times more. Okay, so let's see where that comes from. Let's try to think about that a little bit, okay? In fact, actually, it's a very real effect because you might want twice as big a diamond, but you can't pay 4 times as much, right? That's why there'll be a certain size you can afford. Now, where does that come from? Well, for a diamond to be perfect, okay, it has to push any defects out to the edge of the diamond. And that takes time. The bigger the diamond is, the longer it will take to anneal out any defect and to push it to the edge. And this is why, as they become larger, they become more rare to be very perfect. Okay, now let's turn that upside down. What would upside down be? Upside down would be the smaller the crystal I make, the easier it should be to make it very, very perfect. Right? The cheaper it should be to make, in fact. And that's indeed what happens. It turns out that if we take very small crystals that are only, say, 5 or 10 or 20 or 40 atoms across, it's actually very easy to push all the defects out to the edge and to make them perfect crystals. And therefore, we can make highly perfect materials on the nanoscale, which in macroscopic materials actually are impossible to make perfect. And that's one of the lessons of nanoscience, is we can work with really high-quality material, very low tech. Here's an example of a semiconductor material. These are just tiny crystals. Each one of these is, you can count, each one of those white dots is space between the atoms. You could count how many atoms that is across. And you can see these are all very uniform. And here's a very famous scaling law which shows the energy level of the semiconductor as a function of the size changing very systematically. Now I'll just very quickly try to explain what this is. If I have a piece of solid, I can make an excitation inside it by taking, it's all held together by electrons. I can excite one electron in it. And when that excited electron relaxes back, it emits light. And what you're seeing here is that the emission, the emission of light, the energy at which it emits, the photon energy, depends like 1 over the box size squared. 1 over the size of the crystal squared, that gives the different colors inside here. That's called the quantum size effect, and it happens because an electron is a wave-like particle which feels the edges of the boundary of the crystal. As it gets smaller and smaller, it compresses the electron. You may be familiar, have you ever seen in a museum, you can take a ball and drop it into a funnel-shaped dish, and as it goes in towards the center, it goes faster and faster. If you like, that's what happens inside these tiny crystals. When the electron is in a very small box, it has to move much faster, and as a consequence, the light that it emits will be a higher energy. This has an application. We can take these very small semiconductor crystals, they're only a few nanometers in size, my time is up, and we can put them inside a biological sample and label it. So this shows staining a cell with a very tiny semiconductor. And I'll stop. Just one more slide. 1 minute. This shows an example of a practical application of such a crystal. These are cells which have been stained with quantum dots, small nanocrystals of semiconductor, and here they're stained with an organic dye. And we'll now just turn on the laser in both cases, and what you can see is that the dye bleaches very, very quickly, whereas the inorganic semiconductor does not. And that's a technology that we developed in my research group, which became commercial, and it's available for people to use, biologists who want to do imaging. And so here are some examples of very different colors of quantum dot, different size of crystal labeling. And today, those are very widely used by scientists who want to do things like study cancer cells. Here are some cancer cells attacking a little piece of what looks like a model piece of breast gland, and these are cancer cells. You can see one being labeled green and the other red. That's something that we do in my group, is we develop those kinds of labels. We also develop nanoparticles for many other kinds of applications. And the bottom line on them for you to remember is a very tiny crystal can be made very perfect, but its properties will depend very strongly on the size. Questions? Yes?
Thank you. Well, as a... One moment. Hold on. Hello? Thank you. Yeah, that's a bit loud.
Go for it.
As well, we're all studying electronics, well, most of us, so we're very interested in the application of these semiconductors in electronics. So I wanted to ask, do you think this technology might help overcome Moore's law in the future, and Moore's law's limitations that we see, that electronics can't be scaled down to a certain point in the future, or has this already helped us accelerate the shrinkage of electronics?
Well, let's say that the very small electronics that you have today has to take into account the scaling laws. So, for example, when you try to pass a current through a very small object, you have to take into account the scaling law for the charging energy. The charging energy will be greater the smaller the object is, and that affects the whole way in which the electronics work. So what I would say is, in today's computer chip, the very most recent ones that are being made, the kinds of scaling laws that I described are very much a part of their design. Now, whether that's going to help you make ones which overcome the problems with getting to the bottom of Moore's law, much more complicated, because the only technology we really have that allows us to pattern is really intrinsically tied in with the class of semiconductors that we tend to use. So what I would say is, probably we'll just learn to take advantage of these scaling laws rather than to see them as a disadvantage by changing how we do the electronics. That's my guess.
Thank you.
Mm-hmm. Yes.
Hi. I've watched your lecture about the carbon cycle and about how you can harness the energy of the sun to create fuel.
Mm-hmm.
And I wanted to know if there's been any progress in that area.
Yes. So it's definitely true that instead of wanting to just get electricity from the sun, the best thing would be if we could get energy in terms of fuel. And as you say, the power efficiency of biofuels is quite low, so make artificial photosynthesis. And I would say that there's a lot of progress in that area right now, but there's nothing yet quite ready to go commercial. So it's an exciting moment in that field right now. A lot of developments are taking place. There have been a number of really interesting announcements even in the last year from a number of research groups. So it's gaining momentum, but it's not quite there yet. Yeah.
Third and last question. Yes, Yoel? Just a minute.
Listening to you, marvelous ideas.
Wait a minute.
Okay. Is it time to change the classical curriculum in science education in school and instead start to teach nanotech?
Before you answer, I just want to introduce the gentleman. His name is Joel Rothschild. He is our R&D manager. And what we are doing, I also would like to tell our visitors here that Oort Israel won 2 of the European Union projects, which is NanoU and Nano Channels, to educate about 30,000 students in 20 countries all over Europe with nanotechnology education.
Well, I'm going to answer it indirectly. Let me say this, that one of the most wonderful things about science is its deep unity. All the different parts of science connect with each other in very interesting ways. And one of the reasons I love nanoscience is because it involves a very complex interplay of physics, chemistry, material science, biology, and engineering all mixed together. And I think one of the reasons nanoscience has become such an active field is because scientists from many disciplines really want to have their research play across the unity of science. So that's something I think is very important. But with respect to education, I will say that there's learning math, physics, chemistry, biology, each one is incredibly important. At a certain stage, specializing in one of them is very important. And then at another stage, learning how to move between them is important. So my opinion would be at different stages of education, you know, it's right to engage in different ways. You need to learn the core disciplines, but you also need to learn how to move between them. That would be
Thank you very much indeed.
Thank you very much, Professor Levisatos. It's always a pleasure to listen. Our next speaker is Professor Michael Aschbacher from Caltech, from the California Institute of Technology in California, and he is our laureate in mathematics for classification of finite groups? Finite groups, okay, especially finite simple groups. I like simplicity. Extraordinary in breadth, depth, and beauty. Professor Aschbacher, please.
Well, I'm a mathematician of the old school with primitive presentation techniques here, and I'm not sure the technology still exists for me to use what I have here. Do we have something I can display transparencies on?
We are looking for it.
We're looking for it to look back in time. Well, maybe I'll start talking anyway. So my objective here, I guess, is to try to give you some idea about how mathematicians construct and communicate mathematics. And the way I'll try to do that is by telling you a little bit about these things called groups. I'm a group theorist. So I don't have my slide here to help me, but I'm going to orally give you the definition of what a group is. So groups consists of a set, let's say capital G, together with an operation on this set which satisfies 3 axioms. And since I have only, and I better check when I start here, 8 minutes to talk, I won't tell you what the axioms are. Perhaps we can live without them. But I think I should tell you what an operation is. So an operation on a set is just a rule which, given a pair of elements from the set, spits out another element in the set. So I'm going to, if I have 2 elements, G and H, maybe I'll write G star H for the new element that I get, and I'm going to call that the product of those 2 elements, G and H. And the idea is I'm thinking of this operation as somehow allowing me to multiply together 2 elements in this set. So that's what a group is, except we don't know what the axioms are. Okay? So if I had my slide, I'd I'd show you an example of a group, but I'll just tell you. So the set in this example is the set of integers, which consists of the numbers we count with, 0, 1, 2, so on and so forth, and then the negatives of those numbers, -1, -2, so on and so forth. So that's the set. And then the operation on the set is just ordinary addition of integers. So if you take two integers, n and m, the product of those two integers is the sum of the two integers. Okay, so product is just a word to use here. And if we knew what the group axioms were, then we could easily check that the integers under addition is an example of a group. Okay? Oh, great. Okay. So groups arise in mathematics in lots of different ways. And they're important because of that and because they're useful wherever they arise. See if this works. No? Sort of. But probably the most important way they come up is as the semigroups of objects, particularly mathematical objects. So what's a mathematical object? Well, it could be some mathematical construct that models some sort of real-world situation, or for a mathematician, they're just interesting things in their own right. So typically a mathematical object is a set together with some structure on the set. And since there's so many different types of mathematical objects, it's pretty useless to try to be precise about what the structure is, except we've already seen one example, namely the groups are mathematical objects. The set is the set of elements in the group, and the structure is provided by the group operation. So the next question is, what's a symmetry of an object? And oh yeah. So a symmetry is just a permutation of the elements in this set here that preserve the structure. And since we don't know what the structure is, I can't really tell you what it means to preserve it. But in any given object, I have to tell you precisely what it means to preserve this structure. But still, I haven't told you what a permutation is. A permutation is a rule which assigns to each element in the set another element, let's say f of x, if our rule is called f. And this permutation has the extra property that given any element y in the set, there's exactly one element x such that f of x is equal to y. So somehow we're just renaming the elements in this set using this permutation. Okay? So that's what a symmetry is. You permute around the elements of the set, but in a special sort of way so you preserve the structure, whatever the structure is. I have my cheat sheet here. And I think as it says on the slide, one important symmetry that maybe we'll come to, probably not, is the identity permutation, which let's call it iota, with the property that iota of x is equal to x for every element x in the set. Okay, very special sort of permutation. So where am I? Okay, so finally now, what's the group of symmetries of an object? So it consists of all these symmetries. Supposedly we know what a symmetry is, but we also need an operation on this set of symmetries, and that operation is composition. And on this slide, I think I'm denoting it by a circle. So if I have two symmetries, f and g, what is f circle x? It's just the symmetry defined there. F circle g of x, first you apply g to x, I guess, and then you apply f to g of x. And it turns out that if we'd been careful with our definitions, that this guy, f circle x, would be another symmetry. So now we have our operation, we have our group of symmetries. Okay, so this is maybe the most important way in which groups arise. All right. So let's see. Now we have these groups. What do we do with them? What notions are important when you talk about groups? So probably the two most important notions are the notion of a subgroup and the notion of a representation. So let's see. Do I have a slide? Yeah. We'll just keep talking. So a subgroup is just a little group inside a big group. You take some subset of the group, and you want to make it into a group in a natural way using the operation on the big group. And you can only do that if a nice thing happens. If you take two elements, let's say H and G in the subset H, then the product of these two elements happens to remain inside of H. A priori, it could be anywhere in G. But if whenever we choose two elements in H, the product remains inside of H, then we have a little group inside of the big group, because the axioms on the big group inherit to this small subgroup under that fairly weak property. So one important thing you look at when you look at groups is all its various subgroups. And another important thing you look at is representations of a group. What's a representation? Well, let's see here. Maybe, do I have a slide? Yeah. So a representation somehow is a way to take some abstract group and make it more concrete. So you have this, representation, I think I'm calling it rho there, and what does it do? It assigns to each G in our abstract group a symmetry of some object X, okay? And it has this extra property that you see there, that if we look at rho, we look at G star H, we multiply together these two elements in our group G, we look at rho of that product, it should be the composition of the images of G and H under rho. So if you're a mathematician and you see some kind of equation like that, you should start to feel something right is going on here. There's something attractive, something aesthetically pleasing about that statement. So anyway, the upshot is we're trying to make more concrete this abstract group by representing it as a subgroup of symmetries of this object, okay? So those may be the two most important properties that you look at when you look at these things called groups. So I don't have time to talk about everything on those slides, but the idea is now we take these two notions, this notion of a subgroup and the notion of a representation, and we break our group up into two parts. We take some special sort of subgroup called a normal subgroup, which can be used to define representations of the group. And now we look at the group and we think of it as built up from H, the normal subgroup, and the image of the corresponding representation. So we proceed by divide and conquer. We break our group up into two parts. And we keep doing that. If we can divide each of those parts further, we do so, and we continue along. And here's where finiteness comes in. If there's only a finite number of elements in our group, that process must eventually terminate, and we arrive at some groups, subgroups, or representations of our group, which we can't divide any further. And when we reach that point, the things we've reached are called simple groups. So we've built up our finite group from these simple groups. So these are the building blocks of finite group theory. They're sort of like the primes in arithmetic. You know, any integer can be written uniquely as a product of primes. Well, groups aren't quite that nice. You can't write a group uniquely in terms of simple groups, but there's some nice process by which you describe groups in terms of simple groups. So that's why you want to know the simple groups. So now this award here recognizes a lot of work by me and many other people to determine all the finite simple groups. So write down a list and say that every finite simple group is on this list, and it's an infinite list with many families of simple groups. And the work to try to do this started over a century ago, back in the mid-19th century, and involves the works of hundreds of mathematicians, thousands of pages of mathematics. A very, very complicated piece of work. And a very useful piece of work. So let's see, maybe what sort of things can we take out of this discussion here? So one thing is that, let me see here.
1 minute.
Oh, okay, I'm doing better than I thought. So one thing is mathematicians use language carefully. I mean, I've been forced to cut corners here, but really I should be defining all the words I use carefully and saying things very, very carefully and clearly. That's one thing that characterizes mathematics. Let's see. Another one is that, of course, we see these objects I've been talking about are abstract objects, but it's possible to represent them in more concrete terms and gain intuition from such representations. Let's see, maybe a third thing, a very important thing, is that the value of fundamental research in mathematics, for example, that we can start out with these things called groups, which are defined very simply, but these very simple axioms lead to very complicated structures, infinite numbers of groups, but still with perseverance, working over long periods of time, you can, constructing very complicated machinery, you can eventually determine at least all the simple groups. It's impossible to determine all the finite groups. And once you put in all that effort, then at that point, maybe a century later, you derive important consequences which you couldn't have seen at the start. So when somebody like a president of another university tells you that fundamental research is not important, that you should invest your money in immediate applications, I would say to you that you should think, well, maybe that's not quite right. There's a role for basic research also. Okay, maybe I'll stop here.
Any questions from... I would like to ask you a question. Michael, how did it happen that you became involved in research in mathematics? What happened in your life, you think, which was significant?
I went to Caltech and I took some physics classes and I didn't do as well in them as I would have liked.
Did you have a good teacher in the high school in mathematics?
No.
Did you ask a lot of...
I should say that the physics course I took, at least the last term in quantum mechanics, was from Richard Feynman, who is supposed to be a great teacher. In some ways he was, you know. He had a way of presenting things so that you thought they were very easy. But unfortunately, when you started to think a little more closely, you saw that perhaps they weren't quite as easy as they looked.
Thank you. Thank you very much.
Thank you very much. This year we have 2 laureates in mathematics, and it is my pleasure now to invite Professor Luis Caffarelli from the University of Texas of Austin, Texas, and as his name shows, and as you will soon hear, he comes originally from Argentina. And he has won the Wolf Prize for outstanding work on partial differential equations, in particular on regularity for elliptic and parabolic equations, free boundary problems, and fluid mechanics. Was that right? More or less. Okay. Thank you.
מי שלא יודע, זה כמו שאריאלה מצלצלת, כל פרס זה $100,000.
Can I use the... Of course. I move, I can be free. Yes. This is the one. Okay, thank you very much. Thank you. Okay, so I think I would say that a good chunk of modern science and technology...
Please speak to the microphone.
A good chunk of modern science and technology sort of rests on 3 legs. One, you do the experiment, you do the modeling and simulation, and then you do the prediction, and if the prediction doesn't fit what you expected, you start again and again. And in many areas, in all those areas that involve continuum mechanics, from, let's say, the simulation of a float to the bending of a bar, the mathematics behind it involves a partial differential equation. So, you know, you probably are aware of what I will say, but I will say anyway. So from the beginning of time, people tried to explain qualitative and quantitative the surrounding world. And, you know, first was with discrete methods, and at some At some moment in time, they started to think about instantaneous rate of change. You know, Galileo, Newton, and so on started to create the understanding of, for instance, the idea of velocity as the instantaneous rate of position of a particle, acceleration as the instantaneous rate of change of velocity. And at the beginning, for a bunch of years, they basically just work on system of points. As a typical example is the planetary movement and so on, where what you have is just a finite number of points which are sort of moving and interact among themselves through, for instance, force fields like gravity and so on. And that gave way to a very rich and still very important theory, which is dynamical systems, ordinary differential equations. But about a couple of hundred years ago, more or less, scientists started, sort of engineering-like at the time, started to think of trying to describe the evolution not just of a finite number of particles, but of continuum. For instance, of a piece of an elastic body, of a membrane, of a fluid. And they sort of realized that the way of describing that was to understanding what was the reason why velocities and acceleration change. In other words, they started to relate the rates of change in time with the interaction of a particle with its surrounding infinitesimal particles. In other words, in an elastic body or an elastic membrane, you have the particle you pull, so you sort of may study the interaction of that particle with the very, very, very ones close in space and determine from there what is the effect, the global effect on that body. So, so as I was saying, they did so by connecting velocity, acceleration, with the interaction of a material point under consideration with its infinitesimal surroundings. So that is, you want to explain the vibration of a string, then the string vibrates because it's accelerated by the pull in each particle of the two particles very, very close to them. Okay, or the formation of a body or a viscous flow. So they started to devise mathematical models, right, to describe the evolution of a continuum. So that's what partial differential equations are. So what you have is equations or families equations that involve the infinitesimal rates that relates infinitesimal rates in space and times in an attempt to be able to describe, for instance, if you pull from the boundary, how an elastic body will deform, or how will change the temperature of a bar if you hit the end of the metal bar, or how will the fluid propagate if you inject it into a porous media. Okay? Now let me say something. So what is that we want to know about the partial differential equation? So to say that, let me start by saying sort of that given a phenomena, like there are many different levels of mathematical understanding. Depends how far and how deep you want to go. What are your needs to understand that phenomena? Do you want to know some rough behavior of the phenomena? You need to know a very detailed and deep behavior of the phenomena. For instance, to tell you, okay, I'm going to study water waves. This seems like a fascinating subject. I'm going to try to model it and see what happens. But if I tell you that, all of a sudden you realize, right, that there are many different problems in water waves, right? Like the typical one, the simplest one, is the wave on a channel. If you have a long channel and you make a perturbation at the beginning of the channel, then you will see a water wave that travels very slowly, always the same shape all the time. And this is a relatively, not simple, but a reasonable mathematical problem, okay? But others, you can say, no, well, really what I want to know is the long-term effect on a beach of the waves that constantly, periodically hit the sand, right? And then this is a much complicated mathematical problem requires a much more complex model that in some sense is still related to the original one, because it still is the same periodic way hitting the coast, but you are going sort of through an averaging or homogenization process. Or you can say, you know, this is from our institute in Austin, from a colleague, Clint Dawson. This is a simulation, you know, when there was the oil, the big oil spill in the Gulf. This is a simulation of the spill because of the water waves. So this is still a much larger scale and a much more complex problem. So when you look at a mathematical problem, when you try to model mathematically a phenomena, right, is not just one model that describes everything. You know, there is the complex. You can have many scales of complexity, many layers. So, as I said, this is what I just said, so I won't repeat. So just to give you a flavor of what is a PDE, I just want to give you a little baby model of the formation of a membrane. So I want to start not with PDEs, but I will start with a discrete model. In other words, I said, let's think of a membrane as being a bunch of dots, right, which are joined together by springs. Okay? So you have all these dots and all the springs, and you pull from one side, right, and you want to see what happens. So in this discrete model, right, there are two scales. You can look at this model from nearby, as we are looking now, or you can think of an elastic membrane as looking at this model, having many, many, many dots and springs, and you look from very far away in such a way that the distance between the two consecutive dots are so tiny that you want to think of it as a continuum. Okay? So if you look from nearby, you can try to easily write an equation that says, okay, if I move these four dots a little bit away, this center dot is going to move so much. So you can get an equation for the change of... can you let me know when there is a minute left or something? 1 minute left. 1 minute? Wow, okay. Okay. So you can do an equation point by point, right? But then you can say, okay, so now when I pull from the equation of each point, but what happens on the edge, I should be able to reconstruct the full deformation, okay? And this is what was, I think, in some sense, extraordinary about the theory of partial differential equations. It is that you have a continuum, and for each point, you give an infinitesimal equation, and the knowledge of the infinitesimal equation plus the pooling you have done at the boundary allows you to reconstruct the whole configuration. And I think this was one of the big barriers that the scientists at the time had to overcome. Okay? The other thing is that I did this very simple model, but then you start to think a little bit and you realize that things are not so easy, because if you start to pull, start to pull too much, when there is a big deformation, right, the springs will not respond linearly anymore, right, because the springs will get harder. In other words, you immediately, if you want to look a little bit closer to your model, you have to go to phenomena which are non-linear or more complex, okay? In fact, if you pull too much, the material becomes plastic. The string does not goes back anymore, right? It becomes rigid. And so what you develop is an elastic region and a plastic region. And the difference between the elastic and the plastic is called a free boundary problem, right? Is an unknown curve. If you pull, you can create a fracture. It's another nonlinear problem. If you twist, right, you create dislocation. This is another free boundary problem where you have here inside a hidden surface of dislocation that you have to be able to reconstruct mathematically. Okay? So here is where the perspective of the PDE becomes valuable. In other words, the difference between the discrete and the continuous model is that the continuous model sort of gives you sort of a conceptual understanding of the phenomena that you cannot see in the discrete one. For instance, you can get, you can get in the elastic material, in the continuous case, you can get a much simpler equation. Or you can get, for the elastic-plastic interaction, you can get some sort of description of the moving interface, continuum description, which is much more natural and simple than if you try to do that in the discrete case. So to conclude, let me say that now the possibility of large-scale simulations, right, has brought a symbiosis between the discrete and the continuous. In other words, where you start with the continuous problem, you understand the continuous problem, and that guides how can you discretize that problem to do the computer simulation. In other words, the creation of special elements, the special methods to simulate in a discrete fashion. Like the computer simulation, in some sense, is like turning back to the discrete model, but turning back to the discrete model with a very deep knowledge of how do you have to arrange your dots and your springs. And so let me finish by showing you another of my colleagues, the Center for Computational Geoscience, also at UT Austin. So this is a numerical simulation of the mantle flow, that is the flow just on top of the magma, using a nonlinear Stokes equation. And as you can see, these little triangles are the discretization of the mathematical problem, and it is very much adapted to the a priori knowledge that the PDE, the continuous equation, gives you of the behavior where the flows are complex and you have to refine. So thank you very much for your attention.
כאן יכולנו לראות מודלים מתמטיים לבעיות במכניקה, בזרימה, שמעתם על הכתם הנפט שהיה. מישהו רוצה לשאול שאלות? בבקשה. כן, בבקשה צבי.
Is there progress also in finding analytical solutions, or it's just the way to present the equations to the discrete computation?
Well, I think, until maybe 40 years ago, analytical solutions was basically the only tool. In other words, you could look at the equation and deduce some analytical properties, some formation of discontinuities, the creation of special features. But the main quantitative thing you could say about the PDEs until 40 years ago were just through analytical solutions. I think when numerical simulations came around, everybody thought that that was the demise of analysis of PDEs, but it hasn't been like that, because on the contrary, because you create a mathematical model, right, and then you try to compute it by refining and refining and refining your mesh, right, and you are always far from what you are expect, and that tells you that you have to go and rethink your equation and re-understand what is really going on. And this is what I said at the beginning of this interaction, where you do the experiment and you write a model, and maybe you don't take into consideration, right, the influence of the temperature or of the stress or whatever, and you realize that there are problems with your model no matter how much you refine. And then you have to go back to the mathematics, you have to go back to the experiments and re-understand the mathematics and so on. So I think now there is this interplay in science, that I think is very exciting. Thank you.
Thank you very much. Thank you. As I told you, we have more than 270 laureates from 23 different countries. One of those countries, not always, but many times, is Israel. We have 18, now 19 laureates, Israeli laureates, and it's always a very special treat, and allow me a little local patriotism now, to have an Israeli amongst the laureates. I'll take 1 minute just to explain how these laureates are chosen. Every single year we create a new jury of experts in each field, at least 3, from different continents around the globe, and they receive candidates from us, amongst which they have to decide who is the best of those candidates for that year. Okay, so every year it's a new jury, in every field a different jury. This year's jury in physics has awarded the prize to Professor Yaakov Bekenstein from the Rakach Institute at the Hebrew University in Jerusalem for breakthroughs in the field of black hole dynamics. And I'm sure he's going to tell you all about it. So please, Professor Bekenstein.
אני מציע שהוא ידבר בעברית. יופי, תודה. אני רק עד שהוא מסדר, אני לא יודע מי קרא היום בעיתון, שפרופסור רוקינג בהתחלה אמר שפרופסור בקנשטיין טועה, ואחר כך הוא אמר, סליחה, אני טעיתי, ואתה צודק.
טוב, בוא נתחיל. הנושא זה חורים שחורים. בטח כולכם שמעתם על חורים שחורים, אבל האם שמעתם שזה נושא מאוד ישן? אני רוצה לספר לכם איך זה התפתח, איך זה השתלב בתוך הפיזיקה המודרנית, ונתחיל מיד. הוגי הדעות בקשר לחורים שחורים היו 2, לפלס, מתמטיקאי, אסטרונום ידוע, וג'ון מיטשל, כומר אנגלי שהיה גם גיאולוג ופיזיקאי. אין לי תמונה שלו, אני אדבר על זה אחר כך. הרעיון שלהם היה כזה, אם אתה זורק אבן כלפי מעלה, חוזר, האבן חוזרת. אלא אם כן אתה זורק אותה מספיק מהר שהיא תעבור את מהירות הבריחה מכדור הארץ. היא יכולה לברוח. עכשיו, אם יש כוכב שהוא כל כך צפוף, מסיבי, שמהירות הבריחה יותר גבוה ממהירות האור, אז גם האור לא יוכל לברוח מהכוכב הזה. הכוכב הזה יהיה בלתי נראה. זה היה הרעיון שיש כוכבים בלתי נראים ביקום. אני אראה לכם דוגמה של זה, אבל קודם כל ביחס למיטשל, היות ואין לי תמונה שלו, יש פה מכתב שהוא כתב לקוונדיש, מגלה המימן, והוא מספר פה בדיוק את הרעיון של חור שחור, ואיך אפשר לדעת שיש שם גוף בלתי נראה. המכתב הזה הוא מלפני 230 שנה, זה הגיל של הנושא. החורים השחורים קיימים, והנה הדוגמה. תסתכלו בבקשה על התמונה הזאת. כוכבים במרכז הגלקסיה, מרחק 25,000 שנות אור מאיתנו, עוקפים, זאת אומרת, עושים מסלולים אליפטיים מסביב לאיזה נקודה אדומה, כן, הצלב האדום. התנועה אליפטית מראה שיש פה בצלב איזה גוף אחד שמושך את כל הכוכבים האלה מסביבו, כמו השמש מושכת את הפלנטות במערכת השמש. ובדיוק כמו שאנחנו יודעים לחשב את מסת השמש מתנועת הפלנטות, אפשר לחשב את מסת הגוף בצלב האדום שמה, וזה יוצא 3.5 מיליון מסות של השמש. זאת אומרת, גוף מאוד כבד ובלתי נראה. לא רואים שם כלום. זה חור שחור, ויודעים היום שגלקסיות, כל גלקסיה מכובדת, יש לה חור שחור כבד במרכז, ויש גם חורים שחורים. אגב, חורים שחורים האלה יכולים להגיע לכדי מיליארדי מסות שמש. יש ענקים כאלה. יש גם חורים שחורים קטנים, למשל המנוע מאחורי המקור קרינת רנטגן במזל סיגנוס, סיגנוס זה הברבור, כן? נמצא פה. זה חור שחור עם מסה של 9 מסות שמש, די צנוע. תמונה של המערכת הזאת מהלוויין, מהחללית צ'נדרה, שצילמה את זה בקרני רנטגן, אבל זה כמובן, הצבעים האלה לא אמיתים פה. אתם יכולים לראות איך האובייקט הזה נראה מרחוק. טוב, הלאה. התיאור שנתנו לפלס ומיטשל של חור שחור הוא קצת פרימיטיבי, זה בסך הכל 230 שנה אחורה, אנחנו צריכים את התיאור של התורה המודרנית של יחסות כללית, תורת הגרביטציה של איינשטיין מ-1915, וההתחלה של הנושא של חורים שחורים הוא בעצם בתגלית של האסטרונום הגרמני יהודי שוורצשילד. הוא גילה את הפתרון הראשון הלא פשוט של משוואות איינשטיין של הגרביטציה, מה שנקרא פתרון שוורצשילד. הפתרון הזה מתאר את שדה הכבדה המדויק של גוף כדורי עם מסה M. עכשיו נגיד שהגוף הזה רוצה להתמוטט, מתמוטט מאיזושהי סיבה, זאת אומרת קטן הלאה, בשלב מסוים הוא מגיע לכזה רדיוס שאתה כבר לא יכול לראות את הקריסה מעבר לנקודה הזו, זה פשוט הגוף הזה הוא כבר בלתי נראה, הרדיוס הזה הוא מה שאתם רואים פה, G זה קבוע גרביטציה, C זה מהירות האור, והרדיוס הוא 3 קילומטר לכל מסת שמש בגוף הזה. אם יש מיליארדי מסות שמש, זה בפרופורציה. עכשיו, הגוף הזה הוא כבר חור שחור בשלב הזה, והוא עטוף, בעצם הגבול של החור השחור נקרא אופק המאורעות, משום שאי אפשר לראות מעבר לו, אוקיי? עכשיו, המושג הזה אופק מאורעות באנגלית, event horizon, כבר נכנס לספרות הפופולרית, לקולנוע של מדע בדיוני, יש כל מיני ספרים וכדומה. טוב, נמשיך הלאה בנימה יותר רצינית. אני רוצה להראות לכם פה איזו סימולציה, כשהודיעו שהולכים להדליק את המאיץ הגדול בג'נבה לפני כ3 שנים, אנשים פחדו שיקרה דבר כזה. זאת אומרת שיווצר שם חור שחור שיגדל, יגדל, יגדל על ידי זה שהוא אוכל מסביב את החומר, והוא יאכל את כל צרפת, הוא ייכנס לאוקיינוס האטלנטי, יתפשט, יאכל, יגיע סוף לצפון אמריקה, ואנחנו כבר קרובים מאוד לסוף, אתם רואים את הסוף, כן? זה היה פרדיקציית בלהות של אנשים מסוימים, כמובן זה לא קרה, המאיץ פועל, לא קורה כלום, אבל הסרט הזה מראה עיקרון חשוב, חור שחור יכול רק לגדול, הוא לא יכול לקטון, השטח בגבול של חור השחור נוטה לגדול, זה עיקרון מאוד חשוב לנו, ועכשיו אני רוצה לקשור את הנושא הזה עם הנושא היותר מודרנית, להזכיר לכם העולם שמסביבנו מתפתח בצורה לא הפיכה. למשל, אם אתם מפילים כדור גומי על הרצפה, אז הוא מקפץ, אבל כל פעם בגובה יותר נמוך ויותר נמוך. זה תהליך בלתי הפיך, זה לא קורה הפוך אף פעם. אם אתם מדליקים סיגריה, מי שמעשן, יודעים שהסיגריה בוערת, מתקצרת ובסוף קבע. זה לא קרה אף פעם בסדר הפוך. ואנשים כמובן, או כל בעלי החיים נולדים, אוכלים, גדלים, ואחר כך מתחילים לדוח ובסוף מתים, והתהליך הזה אף פעם לא קרה בסדר הפוך. עכשיו, יש אי רוורסיביליות בטבע, והפיזיקאי הגרמני מהמאה ה-19, קלאוסיוס, מצא איזה דרך מקורית לתאר מה שהעיקרון כאן בלשון מתמטית, והוא אמר ככה, זה נקרא החוק השני של התרמודינמיקה, אם אתם לוקחים מערכת סגורה שלא קולטת אנרגיה ולא מוציאה אנרגיה, האנטרופיה בתוך אותה מערכת, ותכף אני אגדיר, יכולה רק לגדול. מה זה אנטרופיה? אני אסביר איך מחשבים שינויי אנטרופיה. אם יש לי מערכת שקולטת קצת אנרגיה, קצת חום, אני מחלק את הכמות הזאת בטמפרטורה, זה השינוי של אנטרופיה. זה מספיק בשביל שאני אוכל להסביר הלאה את הנושא הזה. עכשיו השאלה, מה קורה עם החוק השני החשוב כשיש חור שחור בסביבה? עכשיו, המנחה שלי לדוקטורט היה ג'ון ווילרד באוניברסיטת פרינסטון, והוא העמיד אותי בפני אפשרות של סתירת חוק השני כשיש חור שחור בסביבה. אתה מכין כוס תה ואתה שופך אותו, יש לו מסה M ואנטרופיה מסוימת, אתה שופך את התה לחור שחור, כמובן המסה של חור השחור גדלת במסה של התה, אבל האנטרופיה נעלמה, ואי אפשר לראות אותה. זה פשוט עניין בלתי הפיך. אז השאלה מה קורה עם חוק השני. אם הוא מופר פה, אז זה הפרה מאוד רצינית, משום שזה חוק מאוד שימושי, משתמשים בו מעבר לפיזיקה, בכימיה, בהנדסה, אפילו שמעתי בכלכלה, יש גם שימושים. זאת אומרת, זה חוק שאתה לא צריך לוותר עליו בקלות, והשאלה הייתה איך להכליל אותו כדי שהוא יחיה עליו בנסיבות האלה. המפתח היה להגדיר מה שנקרא, מה זה האנטרופיה של חור שחור, S של בלק הול, אנטרופיה של חור שחור. והרעיון הוא שהאנטרופיה של חור שחור קיימת, דבר כזה, והיא תמיד מתכונתית לשטח של הגבול של חור השחור, של האופק המאורעות. זה החוק שנקבע. עכשיו, כמובן, שטח היא כמות עם מימדים של אורך בריבוע. אנטרופיה בשביל הפיזיקאי זה מספר טהור. איך אתה הופך שטח למספר טהור? אתה צריך לחלק את השטח בריבוע של איזה אורך קבוע, והנוסחה מקובלת לאנטרופיית חור שחור, רבע שטח של האופק, חלקי הריבוע של מה שנקרא אורך של פלנק, H בה זה הקבוע הקוונטי של פלנק, G הקבוע של ניוטון, C מהירות האור, והאורך הזה הוא מאוד קטן, זאת אומרת האנטרופיה של חור שחור מספר מאוד גדול בדרך כלל. עכשיו, איך אתה בודק שבכלל כל זה סביר, כל זה נכון? יש דרך לבדוק, למשל, אמרתי, השינוי של אנטרופיה הוא שינוי או כמות של אנרגיה שנכנסה לגוף חלקי הטמפרטורה. אפשר להשתמש בנוסחה הזאת התרמודינמית, להגדיר את הטמפרטורה של חור שחור, כי אתה יודע אנטרופיה, אתה יודע את האנרגיה של חור שחור, שזה המסה כפול מהירות האור בריבוע, נכון? לפי איינשטיין. אז בדרך הזו אפשר לקבוע שהטמפרטורה של חור שחור היא הנוסחה הזאת שאתם רואים פה, עוד פעם קבוע של פלנק, המהירות האור קבוע של ניוטון ומסת החור המסוימת. עכשיו, מה פירוש הדבר טמפרטורה של חור שחור? איפה זה משנה? ידוע היום תוצאה מחישוב חשוב של הוקינג. הוקינג זה כמובן הסלב הבריטי שהוא גם פיזיקאי מתמטית בקיימברידג' וזוכה פרס וולף, מזכירים לי פה, זה נכון. הוא פשוט הראה שאם נוצר חור שחור, הראה בצורה קוונטית, אם נוצר חור שחור במסה M, הוא מתחיל מיד לקרון, נגיד, גלים אלקטרומגנטיים של קרינה חומית, זאת אומרת, אופיונית לגוף חם, והטמפרטורה של הקרינה הזאת היא הטמפרטורה הזאת שאנחנו רואים פה. זאת הבדיקה הכי טובה שכל העסק הזה של תרמודינמיקת חורים שחורים, אנטרופיית חור שחור והלאה, הוא עסק שקונסיסטנטי עם עצמו, זאת אומרת עולה בקנה אחד עם העקרונות הפנימיים והחיצוניים. אז זה בעצם הסיפור שרציתי להראות לכם מרעיון מאוד ישן של מיטשל ולפלס, דרך הרעיון של קלאוסיוס על אנטרופיה, אנחנו מגיעים להשתלבות של אובייקטים שהם מאוד מוזרים ובוודאי לא חומר רגיל, ואפשר לשלב אותם בתוך התרמודינמיקה של חומר רגיל.
שאלות בבקשה. בבקשה. כן, כן, זה בעברית.
שלום, אני ניב, אני לומד פה במכללה. עכשיו אני פה עם חברים ואני יודע שהשאלה אולי קצת סוטה מהנושא, אבל מכיוון שאתה מומחה לאסטרונומיה, אז אולי נראה לי שכדאי לנצל את ההזדמנות. היה לנו במשך תקופה מסוימת איזושהי סוגיה עם המרצה שלנו, בעצם הוא ניסה לשכנע אותנו שניל אמסטרונג לא באמת נחת על הירח. ורציתי לשאול אותך אם יש לך דעה בסוגיה הזאת.
מעניין, סוגיה חדשה בשבילי, אבל האמת היא שאני ראיתי את זה בטלוויזיה, זה צריך להיות נכון שהוא נחת.
הוא אומר תראה, היה לו כל מיני טיעונים, אחד מהטיעונים שלו היה באמת שיש שם קרינה קוסמית גם החליפות שלהם, כמה שהן היו מתוחכמות וכמה שהן היו טובות, אי אפשר היה לעבור גם את השכבה של כדור הארץ וגם להגיע לירח ולנחות שם ועוד לחזור מבלי שיקרה איזה שהם נזקים או משהו, בלי למות בגיל צעיר וכל מיני.
יש קרינה, זה נכון, והחליפות הן לא לגמרי עמידות נגד כל קרני הקוסמים, אבל הקרניים הקוסמיות המאוד אנרגטיות שיכולות לחדור, הם נדירים. אז אם אתה מסתובב על פני הירח כמה שעות, זה כנראה לא נורא, לא יותר מסוכן מלהסתובב פה על כדור הארץ שנים. אנחנו גם מקבלים קרינה קוסמית כל שנייה. זה פשוט לא מצטבר למשהו מסוכן עבור רוב האוכלוסייה. חלק מהם כן בסופו של דבר מקבלים סרטן בגלל הקרניים האלה. אז ישנה סכנה שחישבו את הסיכוי שיקרה משהו רע ותפרו את החליפות בהתאם. האנשים האלה היו שם, אני ראיתי אותם, אני זוכר את היום של הנחיתה על כדור על הירח, ואי אפשר להתווכח, היו.
תודה רבה. שאלה, בבקשה, אתה יכול להעביר את המיקרופון?
רציתי לשאול...
תציגי את עצמך.
אני שירן, גם מאורט גלובסקי. רציתי לשאול איך בכלל נוצר החור השחור.
איך נוצר, כן. אם יש גוף יחסית כבד, בדרך כלל גדול, שמשום מה הוא לא עומד בחוזק הגרביטציה, זאת אומרת, הגרביטציה מושכת פנימה, ויש כוחות שעומדים כנגד זה בחומר רגיל, אבל נגיד שהגרביטציה מנצחת, אז הגוף הזה מתחיל לקרוס, ואז שום דבר כבר לא יכול לעצור אותו, קורס, עד שהוא נכנס מתחת לאופק. מעבר לזה כבר אנחנו לא רואים מה שקורה, משערים שהדבר הזה ממשיך להתכווץ עד כמעט נקודה, וברגע הזה חוקי הפיזיקה המוכרים כבר לא, בעצם לא מובנים, לא מתאימים, ולא יודעים מה קורה הלאה, מעבר לנקודה הצפופה הזאת. כנראה החור השחור במרכז הגלקסיה נוצר בדרך קצת אחרת. התחיל כחור שחור קטן מהתמוטטות, הוא ספח כל הזמן חומר מהסביבה, גז, עוד חומרים, כוכבים קטנים אולי, וגדל כל הזמן כמו החור השחור בסימולציה ההיא, בסוף הגיע לכמה מיליוני מסות שמש. אז יש כמה דרכים כנראה ליצירת חורים שחורים.
שאלה אחרונה בבקשה.
שלום, אני דוד.
איפה אתה?
מאורט גלובסקי. יש לי שאלה, יש חשש שנגיד חור שחור כזה יתקרב במידה מסוימת לכדור הארץ עד שיש מצב שהוא יפגע בנו?
כמובן זה יכול לקרות, אבל המשערים שהסיכויים לזה מאוד קטנים ולא צריך לדאוג. יש דברים רעים אחרים שיקרו קודם. למשל, הסיכוי שנתנגש בכוכב רגיל לפני הדבר הזה הוא יותר גדול, וכנראה זה לא קרה גם במשך כל התקופה שאנחנו יודעים עליה. זאת אומרת, יש תמיד סכנות, אבל הסיכוי הסביר הוא שכולכם תחיו חיים ארוכים. אל תדאגו על בתופעות
תשמרו במעבר חצייה.
זה יותר מסוכן, כן.
תודה רבה, באמת תודה רבה פרופסור.
תודה רבה. אישה אחת שמעה הרצאה באסטרופיזיקה, והמרצה אמר שבעוד 80 מיליארד שנה כוכב הלכת שלנו כבר לא יהיה, אז בסוף ההרצאה היא ניגשה אליו כולה רועדת ואמרה לו, כמה אמרת? אז הוא אמר 80 מיליארד. נרגעתי, חשבתי שאמרת 80 מיליון. טוב, עוד דקה אחת בעברית לפני שנחזור לאנגלית. אנחנו, כמו שאתם מבינים, מחלקים, כמו שאמרתי, 8 פרסים, 5 במדעים, 3 בתחומי האמנויות, ברוטציה. המדעים שראינו עד עכשיו זה כימיה, מתמטיקה, פיזיקה, ועכשיו נקשיב לרפואה. התחום החמישי במדעים שלא חולק השנה הוא חקלאות. בשנה הבאה לא יחולק פרס ברפואה, ואם וכאשר נהיה פה, יהיה פה חקלאי שיספר לנו מה הוא עושה וכן הלאה. באומנויות יש לנו שנה אחת במוזיקה, שנה אחת בציור פיסול, שנה אחת באדריכלות וחוזר חלילה. כמו שאתם מבינים, המוזיקאים שלנו לצערנו לא הגיעו השנה, הם חיים מהופעות ואני מנסה לקבוע איתם שהם יגיעו ב-2015. אני מקווה שנצליח.
אם הם יגיעו, יבואו לפה.
כן, אני
במיוחד פלסידו דומינגו.
בואו קודם כל נצליח לקבוע איתם תאריך. Okay, our last laureate for today, not least, is in the field of medicine, Professor Ronald Evans, who is from the Salk Institute in La Jolla, California, and he won the prize for discovering the gene superfamily encoding nuclear receptors and elucidating the mechanism of action of this class of receptors. Professor Evans.
Okay, let's see if this fits on here. Okay, well, thank you, everybody. And what I'm going to do is tell you a little bit about the work from my lab, and it's sort of summarized on here. Is there a pointer up here? Is there a?
I had one up there. So go away. Here.
Oh wait, you don't? No, I don't have one. Okay. All right. No. Okay, there we go. Okay, so what I'm going to do is tell you a little bit about the work that goes on in my lab. What I have here is a slide that illustrates two things. One is the title here, Unlocking Ability, and the password is. And let me just tell you, what is ability? And ability is the capacity to do something. It is the talent to achieve, like what you guys have, or the potential or the power to perform. And you can think of it as maybe a skill to run or to do some kind of particular, anything that you can do can be an ability. But an ability that you may have a genetic capability of performing, like you may have a talent for math. But if you do not study math, and if you do not work with the best mathematicians, it'll hard to be the best mathematician in the world. And if you have the ability to run, if you don't train, you're not going to be able to achieve the potential of that ability. So there's a difference between what you have the potential of and what you actually achieve. And the way that you achieve that has to involve activating the network of genes that involve the control of what abilities are. And that's what my lab does. We use this by studying hormones. Now, the rest of this slide is looking at the iconic DNA double helix, which is shown here, transforming into a tape measure. And the idea of that is that the genes interact with the environment. We bring food and other items into our bodies, and then that gets transformed into nutrients that are shown here that ultimately contribute to the increase of weight. And so if we eat too much food, we will gain weight. And now we're looking at a tape measure here and fats that are being stored in our body as adipose tissue. So I call this balancing the fat equation. How do we control the nutrients coming in so that we're actually in a healthy state and not getting into obesity? Because obesity is driving a large part of the healthcare dollar in our society, and we need to deal with the consequences of obesity, such as diabetes, heart disease, and cancer. Now, what if you could lose weight without dieting? Or what if you could run longer without exercising? Well, these are the areas that we look into. Is it possible at all? As I'll show you, the answer is yes. And if there was a pill that we could develop, would you take it to avoid exercising? Well, it's not so much about you, but it's the ability to create drugs or molecules that manipulate specific genetic pathways that control our body physiology. And so the question here that I'm addressing is, can exercise mimetics substitute for exercise? What are exercise mimetics? Exercise mimetics are drugs that promote the benefits of fitness without actually exercising. And so these are a very interesting class of molecules. And what I'm going to tell you is that this is one of the areas that we first study how muscles work, for example, in the case of physical performance, and then figure out how the gene responds to exercise, and then create sort of a molecular software that activates that genomic hardware. And by doing that, we can manipulate the genome and extract the genomic potential without actually exercising. And that's the question that we're trying to address. And if we can do that, then there's many applications to disease. So this cartoon shows a little PPR delta. This is a genetic switch that we study. This is a cartoon of a switch that interacts with the genome. I'll show you an example of that. This is a drug that we're going to be developing. We call it revving up metabolism. The switch here, this is a PPR delta switch. There's also one called AMP kinase. These are some of the synthetic ligands that we use. This is one, it's called ICAR. And it's a relatively small molecule right here. And let me show you the idea of how we're trying to develop this drug, for example, in muscle. And this is a diagram of a muscle slide showing the nucleus and some fat around it. And the idea of this is you can see the muscle contracting here. We're going to develop a drug that we can give that can find genes in the nucleus where we can activate the switch. And the switch here is going to be activated by a drug called ICAR or PPR delta. This one, these are the drugs coming in. They're going to find sites on DNA where the genetic switch is that we want to activate. This is the actual crystal structure of the switch. This is the actual drug coming in. This is DNA. This is a repressor that keeps all the exercise networks off. Now the drug has come in. It dismisses the repressor, and it's going to recruit an activation process that activates the genes, that allows them to fire. And you'll see that now this gene and a network of genes now begins to fire in a coordinated fashion. This is what happens when you exercise. But now we're doing it in absence of exercise, but actually with a small molecule drug. When you zoom out, you see this whole network of genes that is being activated inside the nucleus. That starts to burn fat away, the muscle contracts, and this fat disappears, even though the animal is not actually exercising. And so we can actually do this. We give mice drugs like this PPR delta drug or the ICAR drug, which is shown here. These are the mice that we have in San Diego, California. We give them these little loungers and small glasses here and eyeglasses. Of course, they need Oakley sunglasses. After some of the mice will get one or the other drug or nothing, we actually do not give them Diet Coke. Then we're going to let them run on a treadmill, and we're going to see how the different animals perform. And we asked an unbiased jury member to tell us what he thinks is going to happen. And so you think you can run? No. So in which case you cannot win the Wolf Prize. All right. So this is what we call the Marathon Mouse Challenge. One of the mice, here, this is a mouse on a treadmill. This is exactly how we run the test. And it's just like a human treadmill. The thing is that they can't get out. And so this is the control mouse, does not get any drug. This is the mouse that got a single injection a day of ICAR. So control and ICAR. And then we basically watch these mice run. We record all this information. We record the oxygen that they use and the energy that's expended. But basically, we're interested in time and distance that they can run. This is a very quantitative experiment. And what you see from this study is that in about an hour and a half, this mouse is completely fatigued. This mouse will run for another hour continuously. And what that means, and it's never been on the treadmill before, it's never been trained, and it is a better performer. The reason it's a better performer is we extract the ability to run, and we actually elevate that to its maximum by giving them a small set of drugs that trigger genetic programs involved in exercise and endurance. Okay, so you can get a Wolf Prize. Now, what's interesting about this study is that within 90 days of the time in which we published this work, these drugs were being used in the Tour de France. And the Tour de France, which was shown here, they found that is in discarded vials along the road, vials of Icar. It was one of 2 new drugs that were being used. And this last month in Spain, the team physician for the Spanish cycling team was found in an airport security check with a briefcase loaded with Icar, which at the time he said, well, it's just, you know, he wasn't going to do anything with the team. It had nothing to do with the team at all. But of course, this has created a big scandal in Spain, and I was asked to comment in the newspapers about it and whether I've created the problem. And so the reality is that we don't create these drugs for athletes, but we do believe that it's possible to create small molecules that we call exercise mimetics in several different ways that can promote health in people who cannot exercise. Many people can't exercise because the elderly, the frail, if you have muscular dystrophy, if you have cystic fibrosis, if you have any kind of injuries, actually obese people have a hard time exercising. So there are very many people, millions and millions of people who are unable to exercise, and these drugs could be very helpful to them. And so if there is a drug, if there is a magic pill, who should get it? That's a big question. Athletes have already decided they should get it first. But you do have to think about the social implications. This kind of medicine would certainly be used by many people who probably it wouldn't be really engineered for, but that's going to be one of the consequences. And studies like this are done by people like you, or hopefully people who will be like you, that will be entering programs in science. This is a picture of the Salk Institute with the installation of a glass sculpture exhibit that we had there. And these are some of the students and postdoctoral fellows that have done this work. So thank you very much. I'm happy to take any questions that you might have.
יופי, פנטסטי. שאלות בבקשה.
Hello. First of all, thank you. My name is Shir. I'm from Otsinger College. And I have a question. When you say it actually helps, but still it's a drug, you know, doesn't it have any effect as a drug, you know, any psychologist problem it causes or something?
Side effects.
Yeah.
Well, many drugs will have side effects. Not all drugs need to have side effects. It really depends on the nature of the drug itself. For example, Icar is actually a natural metabolic product that you produce when you exercise. And so it is the product of burning ATP. ATP is the chemical way in which we store energy. And when you burn ATP, you create AMP. And Icar is a derivative of AMP. So we're giving a natural molecule, which is the signal that you have burned energy. It is what happens is when you exercise. And so we're giving that in a different way, that is when you don't exercise. So normally the only way you get AMP is when you exercise. Now we're giving it when you don't exercise, but the muscle doesn't know that. So it acts as if you are exercising. So it really doesn't have to have a side effect. I mean, it could have a side effect, but it doesn't seem to have a side effect.
So
hi, my name is Maya. I study architecture here. I studied industrial and management engineer before. I want to know if exercising is actually good for you, because there's so many studies that some says that it's good for you and some says that it's not. And from here, it looks like you gave it as a solution for fat. Some people won't gain weight no matter what, for example. Even though I really tried and did so many things to gain weight, I can't. I just can't.
Life's a long time.
So I really want to know if exercise is healthy, or is it...
Exercise is healthy. You don't even have to, I don't finish the question. Studies have shown that people who don't exercise are at much greater risk for all sorts of diseases. And most heart disease, metabolic disease, diabetes is a risk factor. Most people who are diabetic don't exercise. It is also known that if you exercise, even mild walking, if you're diabetic, That is the best medicine. There is no medicine that lowers insulin and sugar better than exercise. If you want to treat yourself, getting good exercise is great, but most diabetics and most people who are obese have trouble exercising at the level that they should. The average minimum exercise for an adult is 40 minutes a day. Very few people get that, and fewer people are getting that, even younger people, because they spend more time on computers. And so sitting and not moving your blood is not good. Most diseases occur by blood that does not move well through the organs like your foot or your kidney or your heart or part of your brain. And so you want to challenge different parts of your body so that they are performing well enough not to get worse. So mild exercise is very good. You don't have to go crazy on exercise, but mild exercise is really a healthful thing.
Thank you very much.
Hi, my name is Nathan from
Where's Nathan? Oh, there you are.
My question is, if you exercise with the drug, does it cause muscle pain and all the effects of exercising?
Oh, if you exercise on top of it. Well, we'll have to ask the athletes that. You know, my view on this particular kind of drug is that it helps people who don't exercise the most. And as you are in better shape, it helps you less and less. Now, athletes are elite, so it's going to help them very little. On the other hand, why do they try it? Any drug helps them only a little, but races are won typically by a little. So these mice, the difference between an hour and a half and an additional hour is gigantic. That's like an 80% increase in performance in the way, depending on how you look at distance or time. But the athletes are looking at 0.5%. That would be happy for them. So they don't really need it, but they may need it to win. And so the point is, it really will help the people who can't exercise at all. And that's a large number of people. And the healthcare dollar, which every country has to pay a large fraction, is a lot of it's going to diabetes, heart disease, and different types of problems that relate to that. And so you want to be able to promote health. And exercise, or possibly exercise mimetics, will be key to that.
Thank you very much. We'll have to stop now, and question will be afterwards. I would like to invite our laureates to have a photograph with us. So any student would like to come with us and making a photograph, it will be on the stage, please. So if you can make a photograph with us, we'll appreciate it. תודה רבה לכם. הרבה תודה שבאתם, ומקווים שנהנתם.